Okay, this is chapter 9, section 1. So this is the last bit of the material for this class. All right, so chapter 9, we're only talking about the section 1, so which is integration by substitution. So remember, so far, when we do anti-differentiation, or when we do integration, it's all simple case, right? We integrate x squared. We see that's x, we add 1 to 2, then divide by 2 plus 1. So that's x cubed divided by 3, then plus c, if it's an indefinite integral. Right? Or we have, maybe you have e to the 2x dx. Then we have e, when we do anti-differentiation, we divide by 2, then plus c. We don't really do this one yet, right? If we have 1 over x dx, when we anti-differentiate, we get ln x plus c. So those are all simple, right? One steps. But remember, when we differentiate, functions, we may differentiate, let's see, x squared plus 2x plus 1 raised by 5. Okay, so how do we differentiate this? We have 2 layers, right? We differentiate by the power. So we say, okay, move the power down and write whatever the inside the expression is. Then subtract the power by 1. But then we have one more step. We multiply by the derivative of inside. So that's called a chain rule. So we have to apply chain rule in this case. So then multiply by the derivative inside, which is 2x plus 2. So now this is, so chapter 9, section 1 is talking about when we do anti-differentiation, right? We go from this to this. So what do we do? So usually we use substitution method. Substitution method. All right, let's see. So we need to be able to recognize the integrand has 2 parts, right? The compositional functions. The integrand, we have f, right? This f is derivative of such f, right? Which takes g as input. Then we do see the derivative of g. Then when we do anti-differentiation, we get f takes g as input plus a constant. Let's see this example. So here we see we have x squared plus 1 raised by 3, then multiply by 2x. So usually what do? We use u substitution, right? We do by substitution. Or could use something else, but normally textbook call this u substitution. So we let u to be the base. So x squared plus 1 to be this, x squared plus 1. As you could think, or maybe you think this as g of x, right? G of x. You think this as f of g of x. Then this part is a g prime of x. Right? Indeed, what's g prime of x? Or u prime. That's just 2x. So usually we call this u substitution. Then we can rewrite this one as u raised by 3, then 2x dx. So when we take a derivative, we have this. So g prime of x equals 2x dx. So 2x dx is just a du, right? U prime. U prime normally we write as du. Then now is with u as variable. So we know exactly how to anti-differentiate this. We add 1 to 3, we divide by the new exponent, then we add c to it. So that's 1/4 of u raised by 4 plus c. Then we substitute u back. U is x squared plus 1. So 1/4 times x squared plus 1 raised by 4 plus c. So that's called u substitution. Or you can call g substitution, right? So in this case, let's see this one. This one saying, okay, let f of x be x cubed, g of x be x squared plus 1. Then the composition function is x squared plus 1 raised by 3. Then g prime of x equals 2x. Then we can anti-differentiate. We see. So we see this one. So this is f of g. This is g prime. Then when we do anti-differentiation, so we get this. So usually called u substitution. So let's see more examples. Let's see this example. So this example is saying set u to be x squared. Oh, this is for the example 1. Right? Example 1 is this. Right? So we let u be x squared plus 1. Then du, right, we differentiate both sides. So take a derivative of this, x squared plus 1. Then, so du equals to this. We take a derivative of this. Then we can rewrite this as 2x dx. You may think this notation is like a weird notation. Let's just take a derivative of this. Remember the related rates, right? Or we could think du dx. So this make better sense. We take a derivative of u in terms of x. You think as u as a function of x. So du dx. Remember before we say dy dx, well, it's same as y prime. In this case, also we can write as u prime. Or write as du dx. Well, du dx is 2x. Then we multiply dx on both sides. So du equals to 2x dx. So we do need to go from this step to this step because we're doing substitution. We want the 2x dx substitute into du because we always have this, right? This could be dt, this could be dx, this could be du, right? So the variable, so this has to be f of u, this has to be f of x, this has to be f of t. So the variables has to align up. Remember, this is a pair. We talk about t, dt, so the t is a variable of the integrand. If we use x, x is the variable of the integrand. So same thing for u, du. So that's why we need to go from this step to this step. To write du, we multiply dx on both sides. Du equal to 2x dx. So in this case, we see this one is u raised by 3. That's this one. Then 2x dx is du, right? Now we're cutting the u-axis infinitely many pieces. So this is our integrand. Right? Now we have the u aligned only with one variable, right? We may not do f of x du, right? This doesn't make any sense. So the variable of the function has to go along with this. Right? Imagine this is a two-dimension thing, right? If this is x, this has to be f of x. If this is a t, this has to be f of t. If this is u, this has to be f of u. So that's why we have to line up all those variables. So u du, we use the power rule to anti-differentiate. Then we substitute back the u value because u equals x squared plus 1. Okay. Let's see this example. So in this case, we see e to the x squared 2x. Okay. If we rewrite this one as e raised by x squared 2x dx. Okay. Then we let u to be the x squared because we see 2x here. Then du equals to 2x dx. Right, so this is our du. And then this one we can write as e raised by u. So we still have valid integral. The integral is e raised by u. Then the x-axis just becomes the u-axis. Then we can differentiate this, right? That's itself. That's e to the u. Anti-differentiate e to the u, that's e to the u. Then plus c. Well, what is u? U is x squared, so substitute back. E to the x squared plus c. Okay, so we let u be x squared. So we differentiate x squared, get 2x dx. Basically, this is du. Then we substitute into this. We anti-differentiate. Let's see this example. So this one, we see this is, well, we want u to be x cubed plus 1. Then we take a du. So du equals 3x squared. 1 derivative becomes 0 dx. So 3x squared dx. So we see 3x squared here, dx here. So we have du. Then this one is the square root of u. Square root of u du, right? Or u raised by half. So half anti-differentiate, half plus 1 divided by half plus 1. Then plus c. Or that's u square root of u divided by 3 halves. Divided by 3 halves is the same as multiplied by 2/3. Then plus c. Then we can substitute the u value back to get back to x. So 2 times x cubed plus 1 square root of x cubed plus 1 divided by 3, then plus c. So in the beginning, maybe you have difficulty to think, okay, which part I want to be u, which part in the integral should I make a u? But you practice, then, you do better and better once you practice on this. Let's see this one. We have ln x squared divided by x, right? So we want the u to be ln x. And then what is the du? Du is 1 over x dx. You see, we have 1 over x dx. Right? So this one can be written as u squared du. But u is ln x, u squared. Then 1 over x dx, that's du. Then we can use power rule. So we got u raised by 3 divided by 3 plus c. Well, u is ln x. So that's ln x raised by 3 divided by 3 plus c. You see ln x, you know the derivative of ln x is 1 over x. Right? That gives you a hint. Let's see this one. We have x squared, we have e raised by x cubed. When you have e term, the u is always going to be the exponent of e. So x cubed. Then du equals to 3x squared dx. Right? But look at this, we have x squared, we have dx, we do not have 3. So we just divide by 3 on both sides. So which means x squared dx equals to 1/3 of du. So because this 3 is not in there, so let's just introduce 1/3. So we can write 1/3 outside the integration sign, right? So have e to the u, then du. So what happened here? So when the integral has e term, all right, we'll always let u to be the exponent of e. So in this case, it's x cubed. So u equals to x cubed. Then take derivative of du with x. So get 3x squared dx. But observe the integral has no 3. Right? We only have x squared dx. So we only have this part. So what do? We divide by 3 here. That only means x squared dx equals to 1/3 of du. So we just pull the 1/3 outside the integration. Then e raised by u, because u is x cubed. Then du. Right? 1/3 of du is x squared dx. Then we can anti-differentiate. Right? Anti-differentiate e to the u, just e to the u itself. Then plus c. Then we substitute back the u value, or u equals to x cubed plus c. You know, once you practice with your homework, you'll get better and better intuition, all right? How to, so to know the u should substitute which part of the integrand. Let's see this one. This one, we see the denominator, square root of 2x squared minus ax plus 1, right? So we want the u to represent that at 2x squared minus ax plus 1. Then we take du. So du equals 4x minus 8. Well, those two has a common factor of 4. So factor out as 4 times x minus, oh, I'm missing the x minus 2 dx. Now we compare with what we have. The inside, we don't have x minus 2. We have 2 minus x dx. So this is, so du equals to 4 times x minus 2 dx. So what do? First, we want to divide by 4 on both sides. Then we want to multiply by negative sign on both sides. Right? So negative 1/4 of du equals to 2 minus x dx. Because we see 2 minus x dx is in the integrand. So we will need to manufacture that. So how do we do it? We divide by 4 to get rid of this 4. Then we put a negative sign. We multiply by -1 on both sides. So now this side becomes 2 minus x dx. Right? It becomes 2 minus x dx, which is included in the integrand. So that only means 2 minus x dx equals to negative quarter du. Again, we're going to put negative quarter before the integration sign. Then we have du. So the inside, what we have? We have 1 over square root of u, right? 2 minus x dx becomes du, well, including this negative 1/4. So remember 1 over square root of u is u raised by negative half. So we use, negative quarter, we use the integration power rule, anti-differentiation power rule, right? 1 over, so this is a half with plus 1. So u raised by negative half plus 1 divided by, well, negative half plus 1 is positive half. So we divide by half. Then we add c. So I'm going to write over here. So that's negative quarter times, well, negative half plus 1 is half, u raised by half, which is square root of u. Divided by half is same as multiply by 2. Right, then plus c. So we have a negative. So this 2, simplify this to be half, negative half square root of u plus c. But now we can substitute the u back. Square root of 2x squared minus ax plus 1. So square root of this. Then plus c. Right. So in this case, the confusing part could be this. Right. So, which part we want to be u? Under the square root. Okay. Above, so the exponent of e, if e is in the integrand, right, the exponent of e is u. If we see square root, so the inside the square root, we want to set to be u. Let's see this example. So the denominator, we have x squared plus 1. So remember, ln x, take derivative, equals 1 over x. If we have ln x squared plus 1, if you take derivative of this, we have 1 over x squared plus 1. But then we multiply this derivative inside, which is 2x. Right? We will have this. So observe this. You see, this is exactly that. So that means when we anti-differentiate, okay, let u to be x squared plus 1. Then du equals 2x dx, right? So we already saw du already. That's du. Then we have 1 over x squared plus 1 becomes 1 over u. This is u raised by, remember 1 over u? The 1 over x comes from ln x, derivative of ln x. But if we do anti-differentiation, that's ln of u. So that's ln of u plus c. Well, u equals x squared plus 1. That's ln x squared plus 1 plus c. X squared is non-negative, so we do not need, so x squared plus 1 at least 1. So we do not need to put an absolute sign there. Okay, for trigonometry, we're going to skip trigonometry ones. All right, that's the last bit of material talking about use u substitution. So one of the integration techniques, use u substitution for the complicated integral.